Alright guys, we're going to talk about graphing and tables today, and this is really your true first video from me. And so I wanted to introduce my little puppy. Well, he's not a puppy, but he's little. His name is Wicket. He gets really bashful when I hold him, and he needs a haircut, but that's my dog, so he's going to hang out with us today. So let's talk about tables. Let me give you an example of an experiment that could be done and where we could actually graph data. So we have an experiment that shows the effect of fertilizer on how big, or the mass of the tomatoes, with the observation that fertilizer X produces a higher mass in tomatoes than other brands of fertilizer. So how is the data going to be communicated? So when we're looking at tables and graphs, the purpose of them is to communicate the data that you collect and to actually formulate an opinion, formulate some kind of analysis and a conclusion based upon what you see in your experiment. So here's a table. If we took the data that we collected and we wanted to make it into a table that anyone in the world could understand, this is how we'd want to do it. You need to clearly label, give your table a title, and it's not just table number 1, it's an actual real title. And it includes the dependent and the independent variable. So you are looking at how does fertilizer affect the mass of tomatoes. That is your independent variable, and then here's your dependent variable. Now if you look at your table, you have 2 columns, and they correspond to the independent and the dependent variable. So you have all of your independent variables matching up with the results that you received. So this fertilizer X yielded this mass, fertilizer Y yielded this mass. And so what this is considered is an ordered pair. Now, a few tips with making tables. You want to have a minimum of 3 trials for accuracy. I may ask you to do more, so just kind of pay attention to what we have going on in class. You could potentially add averages to your trials. You may add more trials to this table, and then at the end you could take all 3 trials and make an average mass of the tomatoes. And then keep your table on one page when you're typing. It should not continue on to the next page. So if it splits, you need to make your table onto the next page. So here's an example of an experiment where 3 trials were conducted, and you can see the average mass for the tomato. So here's the trials for tomato 1, 2, and 3. That's considered 3 different trials. Still have a reflective title, and so these are your dependent, and this is your independent variable represented. And then here you can add the average mass. You don't have to have 12 different tables that represent your information. You can put it all into one table. It's nice and easy to read. Now let's look at how we can graph. If we graph, it makes our data tables so much easier to understand because you want to be able to see trends and patterns throughout your data. And so it's your graph is going to depend upon what type of data that you have. So the first type of graph is a bar graph, and you're going to utilize this when you have ordered pairs that are comparable and are discrete. So the easiest way to remember this is if your independent variable is associated with a number versus a name. So if you're looking at maybe what is the absorbency rate of paper towels? Well, in this case, you're going to be graphing the name of the brand of paper towel and then how much it absorbs. So that's your number versus name. And so you would easily make a bar graph from that. The independent variable is typically all text, or in this case with the paper towels it was a name. And the independent variable is not something that is measurable. So for example, paper towels, or something that is green, blue, yellow, and you want to know how many of something that it happens. That is number versus name. Looking at a line graph, those are probably your really common graphs that you'll use, and that's typically going to be used when something is continuous. So usually time and temperature are very continuous, right? You're going to measure something over a span of 1 hour, and so you take measurements every minute or every 10 minutes, that would be time, or you measure something over temperature. So you're going to see, maybe you're going to measure within, from a temperature of 0 to 20 degrees, and as that changes, you're going to, that's going to be something that's continuous. And so you're looking at two variables that are basically a number versus number, and that's when you can identify the need for a line graph. Remember, in both bar and line graphs, your independent variable is on the x-axis and your dependent variable is on the y-axis. So there is this clue that helps you. The DRY, the dependent responding at y-axis, goes on the y, and then you have at the bottom mix, and so that's your manipulated independent x-axis. So that's where you can identify where the independent or the dependent variable goes. So let's look back at this data. You've got your trials and you've got the average mass. Your independent variable is the type of fertilizer, and your dependent variable is the mass of the tomato. So think for a second, what type of graph do you think we would use? Okay, hopefully you guessed that you're going to utilize a bar graph because you're looking at what type of fertilizer, that's what you manipulate, versus the mass of the tomato, and that is your dependent variable. So here they've represented, all of your fertilizers right here, color-coded it for you, given the trials, and these are just the trials. Now you could take it a step further, and in some cases it's better off to just graph the average because this kind of data, it's kind of hard to see. Now you could tell that the X fertilizer was really successful, but it could be misleading. So if you took a look at the average and just graph the average, then you can actually see a little bit more of a proper trend. Okay, and so notice we've labeled our X and our Y axis. Do not leave these unlabeled. Give a really good title that includes reference to your independent and your dependent variable. And if you use a bar graph, make sure that you color code and you label what those colors represent. Now, let's take a look at a line graph. So the data in the next graph was collected over a period of 7 months, and it looked at plant growth. So the height of the plants was measured in centimeters. So in this case, our independent variable is the 7 months, the time span, and then the plant growth, or the height of the plants, was what was the outcome, the dependent variable. So here would be a table. Again, it has a good proper title, right? Plant growth over time. That's with the independent variable. Oops. Independent variables over here, dependent variables over there, and it's graphed. We do have units. That's very important. Those should be included in your tables and your graphs. So let's look at the graph. In this case, it's a line graph because we're looking at a period of 7 months, and it's continuous, meaning it happens, it happens from month 1 to month 2. It's just continuous. We don't stop, take a break, and then start taking data, next January. We started from January all the way to July. And in this case, we've got the dependent variable over here, the plant height represented with centimeters. And then we do have a nice trend. It's going in a positive correlation, meaning it's trending, its trend is increasing. And so a couple of line graph rules that you should remember. You need to label, and actually this is a good rule for any kind of graph. Label your axis and give units. Always label. Don't leave whoever's looking at your lab experiment. Don't leave them to have to figure it out. Don't make them do the work. Your graph should always start at an origin of 0 and 0. So looking back here, we started with the time at 0 months and at 0 centimeters. If for some reason your graph has a huge break, maybe in its y-axis, actually. Okay, so if you're graphing something, and I'll show you what this squiggle line represents. You're doing 1, 2, 3, all the way across for maybe months. Okay, that's your time in months. Okay, over here, let's stick with plant height. So you've got your centimeters. And let's say that your plants were already pre-grown, and so really their measurements began at like 50 centimeters. You could utilize this squiggle line. It's a break in the graph, and you would actually not graph anything in this region. So your line may start at 50 centimeters and may go up in this manner. You just can't graph anything below that. Okay, and that can be used if that's confusing and you get to that point where your paper, you're numbering up to 1,000 and it's just too much. I can help you understand that a bit better. If your line graph has a true pattern to it, use a line of best fit. Otherwise, you need to connect the dots. So, if your pattern, when you're drawing your points, is pretty consistent and it looks like something that would be a positive line, a straight positive line, take a ruler, or if you know how to use Excel, you need to actually draw a line of best fit, a straight line. It's going to go through the middle and it's basically in a graph almost like an average. If your points on a line graph don't make any sense, you need to connect the dots. Okay? The last type of graph that we should talk about, it's a pretty easy graph to understand. It's a pie chart, and it basically is used when pieces of an entire whole are shown, and the percentages have to add up to 100%. So, for example, here's a table looking at species of whales in a certain location. We want to know what's the percentage of each type of species, or how many species are there represented in this location. And so the scientists went out and counted how many whales of each type of species all the way down. And when you determine the total, then you can do a simple percent calculation. And from that, you can punch out your percentages. These should all equal 100%. Because you're looking at the total population, and so your total population should be 100%, so your value should actually equal 100%. And so all you would do from here is actually make a pie chart, and right here you'll notice all the different percentages are labeled, and if you add this up, it does equal 100%. So this is the best way to show individual pieces that are a part of a whole.